Okay, everyone, we are now streaming live on YouTube. We'll just give it a couple more minutes before we open the conference with some opening remarks. Thanks. Okay, everyone, I think we can get started. First of all, welcome to Dark Matter 2021, from the smallest to the largest scales, hosted virtually, unfortunately, by the Instituto de Física de Cantabria in Santander in northern Spain. This is not the first of these conferences that have been organized by IFCA. In fact, a few years back, there was Dark Matter 2016, summer 2016, and then Dark Matter 2018. And these conferences were really designed to be very broad, covering all topics in dark matter, from theory to experiment, and of course, the phenomenology that bonds the two together. We were hoping, of course, that there would be a Dark Matter 2020, and in fact, we were planning for June 2020 to be the time to do that. But of course, the pandemic had other plans, and so we weren't able to. We had to postpone, and we decided to postpone by a year, in the hopes that the pandemic may have calmed down, the situation might have been better. And so we were hoping to welcome you to Santander, here in northern Spain, to enjoy the city, to enjoy the beaches, to enjoy the life for a week or so. But of course, above all, to enjoy all being in the same place together, to discuss science, to discuss physics, to discuss dark matter, try and come up with new ideas, and also to hear updates about other things that have been going on in the past couple of years. And unfortunately, we haven't been able to do that. And so what we have now is Dark Matter 2021, if I can get my computer to change the slides. Which it will not. Yeah, okay, here we go. So Dark Matter 2021, unfortunately, is entirely virtual. But in some ways, that gives us some advantages. It means that we are able to open it up to a wider number of participants, to participants in a much wider range of geographic areas. So that's great. The problem, of course, is that a lot of us have been sat at home, working from home, and looking at computer screens for a long time, and so it's very hard to concentrate necessarily for a long time in the way that you might have a very, very interactive in-person workshop or conference. And so what we decided to do with this virtual workshop was to kind of pare things back, have a kind of reduced schedule, and really still be able to meet up and have updates on on all the interesting things that have happened in the last few years, but not necessarily have to take up so much time and not necessarily require everyone to be all in the same place at the same time. Okay, and so we have 4 days, 4 afternoons, in fact, 4 invited overview talks, and then a small number of contributed talks. So I see there are already about 100 people watching, about 350, more than 350 registered participants. So that's incredible. Obviously, none of this could have been possible without the help of the Scientific Organizing Committee, who are listed here, who helped us to shape the themes of the workshop, helped to direct us in terms of the best speakers to choose and the best topics to pursue. And of course, the local organizing committee should also be thanked. I'm one of them, but the rest of these wonderful people local here to Santander have done a huge amount of effort in organizing and scheduling and contacting speakers and doing all that. And of course, here we have, this is called local organizing committee. And it's a shame that you all can't be here local to us right now, but hopefully in the next year, in the next couple of years, we can have everybody here in the same place to do the same thing again, but in person. So what's the schedule? So today we have a few hours this afternoon devoted mostly to dark matter direct detection. Tomorrow we'll be covering direct and indirect detection. Wednesday we'll be thinking about accelerator searches for dark matter and also lighter dark matter candidates. And then Thursday we have dark matter and cosmology. And that's a kind of rough division of the different themes of the workshop, but really all of these things are interconnected. Direct detection, it's hard to talk about direct detection without understanding the astrophysical distribution of dark matter. It's hard to talk about very light dark matter without also understanding the cosmology of dark matter. And so we've divided these up thematically, but as we all know, dark matter is such a broad and interconnected topic that this is a loose categorization, let's put it that way. Okay, and the session on Thursday will be slightly longer because we'll have about a 1 hour roundtable discussion. Okay. And so before we start, just a few practical details. So most of you have joined here on Zoom. The links have been sent already by email to the registered participants. We also have set up a Slack and a WonderMe. So WonderMe is a more kind of virtual environment that you can move around in and chat, join different conversations. And so we really encourage you to use both Slack and WonderMe to meet, to discuss, and to carry on the discussion after the talks. Okay, anyone is free to watch on YouTube. We hopefully should be live streaming now. One thing I should definitely stress is that the conference has a code of conduct, so you can follow this link here, or you can find it on the conference webpage. The general idea is just to be respectful of the other participants and to give everyone a chance to contribute and to feel happy and comfortable and safe. And obviously this is a virtual workshop, and so there are some other technical aspects, like please stay muted if you're not contributing, if you're not talking. But otherwise, let's just make sure that everyone has a happy, enjoyable time discussing physics. So if there are any problems, you can email the conference email here, any conference related to conduct or any kind of technical problems with the conference. And then finally, if you find out something new, if you see a great talk, if someone comes up with an idea that you've never heard before that you want to share with the world, please tweet about it, put it on social media, tell your friends, tweet using the hashtag DM2021. Okay, and I think that's everything I had to say from the point of view of the local organizing committee. So unless there are any urgent things from the other local organizers, I'll just say welcome and enjoy. Okay, in that case, if there's nothing else, we can begin with the first talk, which is by Teresa Marodan. So please, if you would like to share your screen.
So I guess
Okay.
I can see it now.
Yes. So the talk is, well, the slot is 50 minutes. So I'll let you know after 40 and then 45 minutes.
Perfect.
Okay.
Yeah.
Go ahead. Thank you.
Thank you. Thank you. Yeah, it is a pleasure for me to have the opportunity to be here and tell you about direct detection. Of course, it would have been fantastic to be in Santander, in this very nice city, but maybe in a few years we can meet in person there. So I'll go directly to a motivation. Looking at the universe, we can make various observations, astronomical, cosmological, that all consistently give a strong evidence for the existence of dark matter. Furthermore, if we look at the measurements of the cosmic microwave background, we can even quantify the amount of dark matter. From the total energy content of the universe, we know that 26% is this dark matter. And this is because we have a model, this Lambda cold dark matter model, that describes very well all the observations that we have. So it looks like a consistent picture. However, the nature, what is the dark matter made out of, is unfortunately not known. No? And this is exactly the question that motivates the searches that I will talk about today. For some of us, the WIMP, the weakly interacting massive particle, is a very favorite or motivated theoretical approach, and a lot of what I will talk about are searches for these WIMPs. However, it's very important to keep in mind that dark matter could be non-weakly interacting, completely different type of particles. And I would touch a little bit on some in my talk, and I believe on Wednesday you will also hear more about this. Now there are these possibilities. So if we are looking for WIMPs, those are heavy particles that would scatter on nuclei, producing a nuclear recoil that you can look at the detector. And if you have light dark matter particles, those can be either absorb or scatter on electrons. And then in this case, you would look for electronic recoils. In both cases, what we are looking at in direct detection are the dark matter particles that are gravitationally bounded with our Milky Way. So we have here our galaxy, and then there is a halo of dark matter particles. And if we now look at the interaction rate in a typical detector, you see here the formula. There are a couple of astrophysical parameters that play a role. For example, because we are measuring at the Earth, we need the dark matter density at this position, and also the velocity distribution of those particles in the galaxy. And the quantities that we are interested on learning about is the cross-section of these dark matter particles with ordinary matter and the dark matter mass. And this cross-section can be spin-dependent or spin-independent, as we will see also later. Now to kind of emphasize a little bit, so in this direct detection method, there are kind of different ingredients that play a role, including the uncertainties. No? In the case of the astrophysics, I mentioned these two quantities. For the particle physics, there are, of course, theory predictions that can guide the direction in which you develop detectors. But at the end, these are the two parameters that you learn about. And there are also nuclear physics aspects that are involved, or atomic aspects if you're scattering on electrons, which result into form factor corrections that you need to know and apply when interpreting the data. Now, kind of generally speaking, okay, what do you need to make a detector searching directly for dark matter? No? So the detector mass is quite important. However, as you will see, this has a range between grams or sub-gram up to several tons. And this depends on the region of parameter space that you are looking at. Generally, you can say the more mass you have, the more target material you have for your WIMPs, the higher the sensitivity. Also, the energy threshold is quite important. So you see it a little bit on this figure, where you see the rate, so the expected rate of events as function of a nuclear recoil scale. Now for different isotopes, so the heavier the isotope, the steeper the curve, but this is a logarithmic scale. So in all cases, you have a kind of a exponentially falling spectrum. So the lower you go with your energy threshold, the more rate you can measure, the more sensitivity you have. No? Typically, you aim to have a few keV or AkeV experiments going beyond that, below that, of course, extremely important, especially when you consider low wind masses. And these have to go together, so the large mass and low threshold with a very, very low background level, and in addition, if possible, also a background discrimination, so a method to distinguish your signal from your background. And now then looking at the signature, so typically you're exactly looking for this kind of spectrum. So this is what most of the experiments do. At the lowest energies, you look for an exponential rise of your rate in the nuclear recoil data. This is, however, not the only possibilities. You can use also a different signature. So if you think about it, you have this halo of dark matter particles in the Milky Way, and the sun is moving. That means that effectively the sun is getting a wind of dark matter particles while it's moving. And now the Earth is moving around the sun, means that for half a year during the year, the velocity vectors of this WIMP wind and Earth, as you see here, are in contrary direction, and then you have a higher recoil energy, and this means higher rate of events, which peaks around June 2nd. In the other half of the year, the worst case, let's say, is in December 2nd, where these two vectors go in the same direction. Then the threshold is effectively higher, and you have less of your rate. And this results in an annual modulation of your rate. So this is also a signature that can be used and is used. And of course, if you think about it, of course, there is a directional dependence of the rate. So if you can measure the direction, you can also identify particles coming from the direction of the WIMP wind. Now, in this slide, which is a bit packed, I put the topic of the background and the reduction strategies. I want to tell that although it is just one slide, this is a topic that keeps us experimentalists in direct detection very busy, because you need a low background, otherwise you don't have sensitivity to look for dark matter. And you see there is a whole variety of sources that can affect your measurement, that disturb you, let's say. There is the natural radioactivity, so the gamma radiation. So you need to select your materials, measuring in Germanium detectors, and choosing cleanermost materials. You can also use shielding to stop those gamma rays. There are also external neutrons, and here there are kind of two sources. One is from the cosmogenic muons, so this is muon-induced neutrons. And for that one, so this is actually the main reason why all these experiments are located in underground laboratories. So you see here how the muon flux kind of goes down, or steeply goes down, with the effective depth. And the deeper you are, the best shielding you have for these muon-induced neutrons. And then there are also neutrons from natural radioactivity, so either alpha-N reaction or fission. This can be fighted by, again, choosing clean materials. The neutrinos from the sun, from the atmosphere, from supernova, are also kind of an external background. I put it here in a different color because although they can also disturb your measurement, they would be also a nice measurement on themselves. No? And finally, there are also internal backgrounds. Those ones are a little bit more detector technology dependent. Typically in liquid and gases, radon emanation is quite important. For solids, surface events, the alpha or beta play an important role, and for all of them, cosmic activation, either of your target or detector materials, has also to be considered. So you see a lot of topics that imply a lot of work before you can start your experiment. Now, once you have a good low background and a good knowledge on your background, and you know how the signal look like, you can run your experiment. You have few events, and the important question is the statistical significance of a signal over the expected background? If you can answer this question with yes, then you have a positive signal, and you can draw a region which is compatible with this number of events and their spectral shape. And it's a region in cross-section and WIMP mass here in logarithmic scale. It could be, for example, a 2 sigma contour of this type. If you answer no, so no significance, then you can place a limit that typically has this V shape. Minimum at a WIMP mass that is often related to the isotope you are using. So, for example, using a lighter isotope would move this minimum to lighter masses. And then other aspects that affect this curve is, for example, the threshold. So you see that towards low WIMP masses, the threshold makes that the curve very, very steeply goes up. So you lose sensitivity, and you see why lowering the threshold not only opens you new dark matter masses, but also over the whole mass is an increase on sensitivity. And then just to go down in sensitivity, you need to collect exposure. This means large target mass or measuring time, more years of measuring. Before we go into details, I want to give you an overview of how this would look like. You will see many plots of this type, but it's most of the times the same thing. You have here the spin-independent cross-sections of WIMPs with nucleons running over several orders of magnitude, and then the WIMP mass, and all these more or less V-shaped exclusion limits from all these different experiments. We will learn that for kind of high WIMP masses of above a few or so GeVs, novel liquid detectors, especially xenon ones, are the most competitive. And then down here, there is a lot of activity, even more than what is shown here from this particle data group, from bolometers, gaseous detectors, many, many things. And what is often also shown here are this color region, and this represents the cross-sections at which neutrinos start interacting coherently with nuclei, and then they also make nuclear recoil. So it's the same kind of signature, and it's kind of seen as a limit towards which it might get difficult to distinguish dark matter from neutrinos. Now, here on the low WIMP masses are the solar neutrinos, which play a role, and up here, both atmospheric and supernova neutrinos are the ones that play the role. So this would be for the WIMP searches. But I said before that there is also the dark matter scattering of electrons. And you see that here there are different experiments, especially the ones with very low threshold that play an important role. So these figures in this case are from the Sensei technology using silicon CCDs that we will discuss later. And you see that now we are not anymore proving dark matter masses on GeVs or so, but we are testing MEV energies, masses. And here you have an example for a heavy mediator and a light mediator on these two plots. Now the WIMP or scattering on electrons, when you have a nuclear recoil or an electronic recoil moving through a target medium, you have different possibilities. So you can have phonons or HIT if you have bolometers or superheated liquids. You can have scintillation light for scintillator crystals or noble liquid gases, or you can have charge ionization, either in germanium or gaseous detectors. Here, it's especially good if you have not only one, but two of these signals, for example, combining phonons and charge, or phonons and light, or light and charge, because then the ratio of these signals is typically different for different types of particles. And this gives you a handle to suppress your background. So you can separate nuclear recalls from electronic recalls by combining different types of signals. Now, the plan of my talk from now on is to kind of drive you through these different technologies, briefly explain you how it works, and then mention a couple of important results of the last couple of years or important results in the field. But I think it's quite important to mention that, as a kind of disclaimer, that this is a selection. So I'm sorry if I cannot bring all the experiments that are around, because there are many. So I tried to make the best, I hopefully not too biased selection of results and topics. And the structure would be such that I will start with solid detectors, then I will go to liquid, and then to gas, such that you can follow a little bit on that. And starting with the solids, I need to talk first about signal of dark matter. This is the DAMA experiment, who uses a very clean sodium iodine crystal. It's running at LNGS in Italy already since 20 years or so. So they look for the signature that I mentioned before, so an annual modulation of the background at the low energies. And you see here that exactly this is what they observe. No? The rate that goes up in June, down in December over all the cycles. And because they have been measured over all these years, they have a very high significance. And there were news this year on the experiment. So in July at the EPS conference, they presented an update of the data with more exposure and energy threshold lowered to 0.75 keV, which increases then their significance to 13.7. So it's a very clear signal. However, this is a little bit controversial in the field, because the kind of WIMP interpretation of the signal is in contradiction with many results worldwide. So if you have a look on here, in this figure, these close regions are the cross sections and masses that are compatible with the signal that DAMA sees, but it is excluded by many experiments by several orders of magnitude going down. And even if you go in that direction, also almost an order of magnitude in the threshold. No? So it's an open question, what DAMA is observing? And the point is that most of these results shown here are not using exactly the same technology as DAMA, and that's why there is a whole effort worldwide, so you see it here, to build detectors that use also sodium iodine to be able to check if this signal is also observed. No? You see several of them here. I think tomorrow you will hear about Sabre. Myself, I will concentrate on two results of this year, actually, so quite fresh news. One of them is cosine 100, which is an experiment in Korea. With the data they had, they can exclude. So when they make let's say an interpretation of the data as being due to WIMPs, they can exclude the signal of DAMA. However, when they perform an annual modulation in the same way that DAMA does, they are both compatible with no modulation and also with DAMA. So unfortunately, not yet very conclusive on that. However, we can be lucky that there is the Ionization experiment. I think you will also hear tomorrow more details on that. This is an experiment running at the Canfranc Underground Laboratory in Spain, in the Pyrenees. And you see here their 1 sigma, 2 sigma, and 3 sigma, and the data points that they have been measuring. And you can compare that with the DAMA Libra amplitude. And they have, in the latest result that they release in this publication, they find 3.3 sigma for no discrepancy with the Gamma Libra signal when they look at the 1 to 6 keV, and the 2.6 sigma when they look at the 2 to 6 keV. No? So it looks that there is quite some tension on there. For this measurement, actually, the sensitivity is below 3 sigma, but in the next years, they will be above, and they could make a very clear statement about the gamma signal. So the next technology I want to talk about is the cryogenic polymeters. Those are crystals that you cool down to millikelvin temperature, and then an energy deposition by a particle and moving through. So this crystal would produce phonons, so heat, and then you can measure this increase in temperature. And this is tiny. So if you think about a Germanium detector as this 20 millikelvin, and you consider a few keV nuclear recoil, you expect about 20 microkelvin increase in temperature. And this is the reason why you need to go to these very cold temperatures. You measure this increase in temperature by different technologies, NTDs of TES. Maybe I don't go into detail. But as I mentioned before, if you combine the phonon measurement with either light or charged readout, then you achieve this very good separation of your background of electronic recoils from the nuclear recoil signal you're looking at. And here is an example from the CREST experiment. On the bottom are the bands where you would expect your nuclear recoils, and here is the background. So you're far away, and then you can make a very clean kind of measurement of that. Here you see one of the examples of these detectors. CREST, Edelweiss, and Super CDMS are all these kind of bolometers. They have excellent sensitivities, especially at low WIMP masses. And this is due to the very low energy threshold that they can reach. No? So you see here, 30, 70 electron volts, so really low. And there is from CDMS, there is even news, because they have developed a technology with which, using actually a very small mass, but a very, very low threshold, they can reach an excellent sensitivity. And I believe in the talk after that, you will hear more details, so I probably don't need to tell you now more on that. I just saw you here the figure from the CREST collaboration, where you see kind of the potential of this technology. We have again the same plot, but now we are zooming into the low WIMP mass region. So the liquid noble gas limits are out of range here. And then you see how nicely the CREST limit enters to very, very low, down to 100 MeV or so. No? And it's similar for other of these bolometers that can explore this region that is otherwise not reachable by other technologies. There is also germanium detectors that are measuring dark matter. They have the advantage that they are very clean in terms of radio purity and also low threshold. And in addition, a very good energy resolution. And this is nice because then you can identify all the lines of your background, and this helps you to suppress the background if you know what are the composition. On the con side, there is no particle discrimination, so you cannot distinguish if this is now nuclear recoils or electronic recoils. An example of this technology is the SEDEX experiment at Jinping in China. Here you see a photograph, and on the right, you see again, zooming into the low WIMP masses, the result that they published a couple of years ago. Now you have to be careful, because in this work, the Migdal effect was used. And you see also here result from Edelweiss, you see the Migdal effect, or LUX. So maybe we make now a short excursion to try to understand what this Migdal effect is. So until now, or until a few years ago, it was seen in that way that once the dark matter scatters on your nuclei, the whole atom moves and is slowed down by the medium. However, in a paper that came out in 2018, pointed out that actually you kick on the nucleus moves, and then the shell electrons kind of feel this electromagnetic impulse and follow the nucleus. And in this process, electrons can be excited or ionized. No? This is something that is predicted this way, is seen in other kind of processes, but so far there is no experimental evidence of this effect. So we expect that it happens, but it's not measured. And that's why at the moment, I think one has to take this Michel effect results with a bit of care, because only once it's confirmed, we can take it kind of more seriously. But there is quite an effort to try to measure it. So there are specifically collaboration, the Michel collaboration, and also a group in Japan trying with low pressure gaseous detectors to really see this effect in order to be used in dark matter searches. And then I also wanted to mention these low threshold searches with CCDs. And there is, as you see here, lots of activities. I give you here some figures of detectors that are around using this technology, but you will hear a lot of details, I think, from Damiket and DM Square in this conference. What is very interesting is that those are actually gram scale devices with really, really low threshold. And this allows you to also test this region of low wind masses, or this region of electron scattering. For example, the plots that I showed you earlier were from the Sensei collaboration. And in addition, they have a very nice feature that you can reconstruct tracks of particles in 3 dimensions. And you see here an image that I took from Damiket, where you nicely see how an alpha deposits the energy, a muon, or an electron. You know, and this allows, of course, also for background suppression. They aim at measuring dark matter electron scattering down to 1 MeV and this low wind region. So this brings me to the liquid detectors, and I start with the liquid noble gases, which are very attractive technologies because you can really reach a very large and homogeneous targets. In principle, you can have all neon, argon, and xenon. However, effectively, argon and xenon are the ones that are being used. The technology allows to reconstruct the position of the event, and then you can select an innermost volume. This is clean, that is clean in radioactivity for analysis. This is what we call feed visualization. And at the same time, they are transparent to their own scintillation light, so you can kind of easily scale up without losing so much of the signal. And in using liquid noble gases, you have kind of 2 technologies. The first of them is the single phase, so liquid. And what you have there is most of the times a sphere filled with the liquid, and then photosensors that can cover almost 4 pi of the surface. And with this, you have a very, very good light collection that gives you also very low threshold. And here, you do not employ combination of different signals for background suppression, but you can use the pulse shape to separate. No? For example, the decay time constants of the scintillation light are very different in argon and neon for the triplet and singlet states, and those are populated differently for nuclear recoils and electronic recoils. And you see here an example how an electron recoil would look like, or an alpha particle by a liquid argon experiment, RDM. And using this kind of trick, you can reach particle separation all the way to 10 to the 8, for instance. This was what deep reach. This can be also used in xenon. However, the scintillation constant are closer to each other and is a little bit less powerful, but still has been used by the X-Mars collaboration to derive physics out of it. Go a little bit more in detail into the DIP experiment, which is a ton scale liquid argon detector at Snolab in Canada with 3.6 kilograms, 3.6 tons total mass, and you see here the fiducial volume. The latest results are from 2 years ago of 230 days. And you see here the R² set distribution of their events. You see all of them are at a very large radius, and the fiducial volume represented by this blue line is empty. And they derive an exclusion limit, which is actually the most competitive liquid argon result by now. It's this red line that you have here. And what I understand is that they kept on taking data, and there is a whole run which is being analyzed, so some news might be coming soon. In that run, there was some limitation from some contamination at the top of the detector, but this is being addressed, and some improvements will come. There is also talk about the experiment where you will learn all what I said very quickly in more detail later on. So the second type of technology with liquid noble gases is the two-phase Tpc. Here, the target is still liquid. It's a big volume of liquid, but you have a gas on the top. This is because when a WIMP comes in, you have your nuclear recoil moving. You still have the scintillation light that you have a look with photosensors at top and bottom. But in this case, you build an electric field such that the created charges are drifted through the liquid, extracted to the gas, and the gas is used for a secondary signal that we call STU. And then we have these two signals that can be now used to separate electronic recoils from nuclear recoils. And here is an example. An electron, here from a gamma, would have these sizes for S1 and S2, and WIMP, in this case, was a neutron. The relative size is different. And this is one advantage of this technology. The other one is that you can very precisely reconstruct the position of the event using the PMT pattern, but also the drift time. Then in all X, Y, and Z, you have your position to select your fiducial volume. Now, DarkSide is an experiment of this type. DarkSide 50 was a detector, or is a detector that runs at LNGS with 50 kilograms of mass, and nice results have been derived from this data. And afterwards, the liquid argon community joined forces together. So DarkSide joined DEEP and RDM and a few others to go together in a new global collaboration, and they aim at a very large detector of 50 tons. This is DarkSide 20, which has here a very new design in an acrylic vessel, all read out by silicon PM, so very large surfaces of silicon PM that is right now being developed. Quite important for argon is to get what is called underground argon, because if you take the argon from the atmosphere, there is an isotope, Argon 39, that would be creating signals all the time and would create a lot of death time for your detector. And that's why the argon is now taken from underground, where you have less production of Argon 39 or negligible. And this is taken with a plant, an Urania plant in Colorado. Then the argon that is extracted there comes to Spain, to the Canfranc laboratory, is measured the depletion factor, and from there it goes to Sardinia to be distillated such that you even suppress more Argon 39, and at the end you end up ideally with a factor about thousands or so less Argon 39. Overall, the experiment aim DarkSide 20K to be very competitive at high masses. So they measure between 20 keV and 200, and they will be in operation, or the plan to be operating in 2025. And in between, they are developing a prototype to demonstrate all these new technologies that is planned to be operating in 2022. You see here what I described so far. So this was a result of DarkSide 50. They also made a special analysis using the charge signal only that give also sensitivity to lower WIMP masses, and indeed in a certain region of parameter space they have the best sensitivity. And from here, the plan with 20K is to go to this here. And they even make the plans for longer term, even a larger detector Argon is being studied or considered with this kind of fiducial mass, and also a detector targeting for the low point masses is being developed. There is also a talk today, and I think you will learn a little bit more on all this dark side effort. Now I move to xenon, and maybe I should start saying that I'm a member of the xenon collaboration, such that you understand why I'm so proud of all the results that we have. Indeed, above 3 or so GeV, the results of our experiment have the best sensitivity, so no measurement of dark matter, but at least the best limit worldwide. You see here what I said, this is the region of dark side, and then below, to be taken with care, this Migdal result, but most importantly, this CREST result in other bolometers. Xenon 1 ton, which are the results I'm showing you here, was operated in Gran Sasso at LNGS from 2016 to 2019. And then afterwards, we moved to the upgrade. Something that I should mention, which was quite interesting last year, was a signal that we found. Now, all the results that I show you here are kind of looking at the nuclear recoil, the WIMP searches, let's say. But we also had a look at the electronic recoils. There, typically, we fit all the components of our background, and you see here the dashed lines, all what we know of our background. We are dominated by radon emanation, we have krypton, we have several lines, and so on. And we understand very well. But once you zoom in into the lowest energies, you see this rate rising up. No? It's not very significant, but it's 3.3 sigma, and above 3 sigma we report results. And this indeed created a whole excitement in the community. A lot of publications trying to explain our data either as a new background or as a new signal. We indeed spent a lot of time on trying to understand if there is a new background. We thought tritium would be. From our studies, it doesn't look to be the case, but there are several unknowns on that. Of course, it would be extremely exciting if this signal would be the first indication of something new physics, solar action signal, some neutrino magnetic moment, maybe something else. So the situation remains quite exciting for us, and in our update in Xenon N-ton, we aim at testing exactly this axis. But we are not the only ones. So in liquid xenon, there is a very strong competition. There is LZ in the US, Panda X in China, and ourselves. All of them kind of similar. Panda has released some data. LZ is commissioning. We are taking data. So you can really say this is a race to be the first to measure WIMPs down to this kind of cross-section. As I mentioned, there were results of Panda X this year, so quite exciting, of course. They have now is the largest detector that have results. Unfortunately, they had a little bit of contamination with tritium because they calibrated with tritium their detector in the previous phase, and then the same xenon was used. So they have this, and they need to purify it. The radon level is well understood at the level similar to Xenon 1 ton. And you see here the sensitivity and the result in red. Unfortunately, they perform a non-blind analysis, which is not kind of the standard in the field, but for the next run, they plan to do a pure blind analysis. And I think quite important to mention is that indeed in the direct detection community, there are some joint forces into the statistical treatment with the goal of have conventions, recommendations on how to treat the data. And part of it is the use of a blind or a salted analysis. And this is something we all aim at. For xenon enton, as I said, we are taking data, and we have shown in the last conferences a bit on the performance. So here you see the spectrum, which is blinded at low energies for the low ER excess and for the WIMP surge, at high energies for the double beta decay. We are very proud of our background level. So we reach already 1.7 microbecquerel per kilogram. And we know that we can reach another factor of 2 if we change our distillation column. So we really would get the goal both in radon and krypton. And you should hear some news from us in a few months. And just to mention, we are also planning the future. The Darwin Detector, so it's a larger scale with 50 tons of liquid xenon, ideally to measure the WIMP properties, and if not, then to have an ultimate sensitivity to the cross-section of WIMPs with nuclei. And the nice thing once you have this very, very large detector is that new physics become available: solar neutrinos, supernova neutrinos, coherent scattering, proton decay, rare decays, neutrino-less double beta, double electron capture. So it's quite exciting project. And it aims to go from what xenon enton and LZ aim at, so another of magnitude below. And what is maybe interesting for you to know is that while right now xenon and LZ are competitors, we have already gathered together with a common workshop with the idea that in future, xenon, LZ, and Darwin will go all together to build this large detector in order to combine the expertise of all of us.
Sorry to interrupt. You've had about 40 minutes so far, so there's 10 minutes left in the total time.
Very good. Another liquid technology that is quite interesting is the superheated fluid detectors. So this is a bubble chamber that was used in the past in accelerators. Now it's a kind of rediscover for dark matter. So dark matter introducts and you get a bubble. And this bubble expands and you can make a photograph of it. And what you use to distinguish it from background, in this case, the background is from alpha particles, is that the sound of these bubbles is different. So here you see for alphas, this red region, they have acoustic power that is significantly higher than for nuclear records. And the PICO experiment has used this technology, very successful. And they were running until 2017 at Snolab, and now there are upgrade detectors being developed. PICO 40 is a kind of a technology demonstrator, but because of the lower background, they will be compatible on the physics reach with PICO 60 or even go beyond. And PICO 500 is kind of the larger experiment being planned to be built at Snolab in the future years. What is important of this experiment is, although it is not as large as, for example, the xenon or the argon I talk about, they are quite competitive because they have a very good sensitivity to spin-dependent interactions. So you see here the PICO 60 result and the PICO 500, what they aim at, and it's quite similar to what, for example, LZ would reach. Now, so I said before, so dark matter can couple to the nuclear mass. In this case, you have this spin independent. This is most of the plots I have shown until now. But if you now couple to the nuclear spin that is carried out either by the protons or by the neutrons, then you have this spin-dependent case. And here it depends on how many isotopes in your target have a nuclear spin and how large is the spin expectation value. In the case of PICO, they are very convenient because they have fluorine, which has a very high value. And you see here in the WIMP proton, they are really dominating the sensitivity, and the WIMP neutron is the liquid xenon that have the best sensitivity. And finally, I move to the gaseous detectors. I start with the directional searches. Here, so if you consider solids of liquids and a few keV nuclear recoil, the range of the nucleus is about 100 nanometers or so. So this is really small and difficult to reconstruct. But if you instead use a low pressure gas, something below 100 torr or so, then the range is 1-2 millimeters, and then this is something you can measure in a gas detector. So most of the experiments using this technology are low pressure TPCs using CH4. Now you have fluorine again, which is convenient for spin-dependent searches. And they look exactly for this small track that drifts charges into the readout plane and try to measure that, which is of course quite a challenge because it's still a millimeter track. And when you want to go large in mass, you have a large volume, typically of cubic meters and so on. And this challenge to reconstruct it. They are right now not competitive with liquids or solid, but it will be in future a very important technology in order to confirm that when you're measuring an excess, that this is really coming for the wind. Important technology demonstrator was Drift, an experiment that was running in Bolby, which had a cubic meter, and was the experiment that produced also results or dark matter limits, and they operated a large scale kind of detector. And Drift, together with many others that I listed here, have built now a worldwide proto-collaboration under the name of Cygnus to measure both dark matter, but also coherent neutrino scattering from solar neutrinos, exploiting exactly this directionality and particle identification that you can do when you have these tracks. Here, note, there is actually also directional searches using nuclear emulsion. This is, of course, not gas, but I wanted to briefly measure that this is also being developed.
Sorry, we have about 5 minutes left in the total time. So if you'd like to wrap up so we can leave some time for questions, thank you.
Yes. This is actually my last slide on experiment, the UNIUS-G, which is a gaseous experiment in a metallic vessel with a central anode in the middle, and also in this case, very, very low threshold. That's why the small mass is not a problem, so you still can be very competitive at low wind masses. The recent news is that they have a new sphere of 140 centimeters that was operated in Modan. The 12 days of data that they took is being analyzed. And afterwards, it was moved to Snolab. I think the construction of all the shield and everything finished in just this August, so a couple of weeks ago. And in the Taub, we saw even a first pulse coming from this experiment. And with this, I'm actually already in my summary slide. What I'm showing you here is not anymore the results that exist right now, but the green region is kind of the current limits, and all what is shown now is like the projections for the future. No? So we will hear a lot of new results in the upcoming years on this region, mainly from Argon and xenon experiments, and here from all these various technologies, which are very interesting, bolometers, CCDs, gaseous detectors that will prove all the region here. So you see dark matter direct detection covers a very large range in cross-section and in mass. We are mainly exploring WIMPs, but we also look for other candidates like dark matter, axion light particles, dark photons. So there are also some potential on this side. And what we aim at is dark matter discovery. So this would really be the nicest thing, and ideally in various detectors such that we can combine the information and learn something about the properties of this particle. Thank you very much for your attention.
Thank you very much, Teresa, for this great and comprehensive overview of dark matter direct searches. If there are any questions, you can raise your hand using the reactions button. I think we have a couple of minutes. A moment. Yes, go ahead, Sven.
Hi, Teresa. Thanks for this great overview. This axis that you've shown from your own experiment at low energies, what about the other xenon-based experiments? Shouldn't they be sensitive to it, or Do they say something? Could they say something, or what do we expect in the near future from them?
No, this is a good question. I mean, Panda-X, unfortunately, with the data they have so far, they are not able, because they have the tritium inside. And tritium, I mean, it's exactly the shape. No? Once they manage to get out the tritium out of it, then they could test, but for the moment, not. LSAT, they should be able, I mean, they are as large as xenon Anton, and when they acquire a few months, they of course would be able, and this would be a very important test, of course, no? Because depending on what we see in xenon Anton, if we see it again, then it's very important if another liquid xenon detector sees or not to kind of verify. No?
Yeah. Okay, thanks a lot.
Yeah, you're welcome.
Do we have another very quick question? Yes, go ahead, Chema.
Hi, Teresa. Thank you for your talk. Very nice. So, what's your feeling? I mean, seeing as you are, that the space is running out, and there is no clear evidence yet for WIMPs. What do you think is next?
Yeah, this is a kind of difficult question to answer, no? I mean, you're right, no? The WIMP is getting into a tight situation. Of course, the large experiments like xenon and argon want to explore the parameter space down, no? Because we believe these technologies are able to do so, and it's of course not yet excluded that something would pop up there. On the other hand, as you say, it's important to keep a bit open on other regions, no? And I think this is exactly what many R&D activities are going into. No? For example, this low mass region was kind of ignored 10 years ago, and now there is such an effort on technological developments to measure there. And actually also us, no? DarkSide ourselves, we use this special analysis with only charge, or we look for this Migdal effect, or we try to develop detectors with even lower threshold, such that we can open, let's say, in that direction, no? Or we look at the electronic recalls like we are doing here. This is unfortunately a background dominated region, but if you have a good control of your background, you can also look for candidates there. No? So there are kind of efforts into extending from the WIMP to other candidates, because it makes completely sense.
Thanks.
You're welcome.
Okay, I think we probably have to stop there and move on, but we can certainly thank Teresa again. Thank you very much. And I think if people have more questions, they can go on the Slack, and hopefully you can answer some of those. Okay, next up we have Tarek, if you would like to share your screen.
Yep. All right.
Okay, so the total time for the talk is 20 minutes. So I'll give you I'll let you know when 15 minutes and then 17 minutes have gone. Thanks.
Thank you, Bradley. So I certainly appreciate the opportunity to talk to this group about the Super CDMS Snolab experiment and sort of the range of science that we hope to be able to achieve with that experiment. Let's see, where's my clicker? So, and I should, by the way, start by thanking Teresa for an excellent overview talk of dark matter. It makes my job, and I'm sure the subsequent speakers' jobs easier. So I'm just going to dive right into talking about the Super CDMS detectors and a little bit about the principles behind how they work and how we can use them to sort of push the frontiers of sensitivity and cross-section and in mass. And then I'll put this in the context of the Snolab experiment that's currently under construction, and try to kind of end on a note of where are the current status, the scientific status of Super CDMS, and where we hope to be in the next few years. All right, so starting off, this is a picture of the Super CDMS collaboration from a couple of years ago when we were allowed to leave our homes. It's a collaboration of about 30 institutions and national labs from around the globe. There we go. So diving straight into the detectors. Super CDMS, as was indicated previously, we use solid-state detectors. Namely, these are crystals of silicon and germanium. And for those of you who have heard, or are familiar with the experiment a bit, you've probably heard of them referred to as IZIP and HV. These are technical jargony names. I will, for the purpose of this talk, refer to them as low background and low threshold detectors, and I'll explain the difference very shortly. But the idea behind how they work is fairly straightforward. Namely, you have a crystal, and when a particle comes in and interacts, it'll deposit a certain amount of energy, and that energy appears in two channels, namely a population of phonons and a population of electrons and holes. Now, we apply an electric field across the crystal, and that will allow the electrons and holes to drift to opposite sides where they can be measured by a charge amplifier circuit. So this gives you one measure of the interaction's energy. However, at the same time as this is happening, the phonons are bouncing around the crystal, and they eventually make it to the surfaces where we have another set of sensors. These are transition edge sensor devices that measure the energy in the phonon system, and that'll give you an independent measure of the energy of the interaction. So why do you go to the trouble of measuring the same quantity twice? Well, because as was indicated earlier, there is information in there beyond simply the energy. Namely, you're able to extract information about the type of recoil, whether it's an electron recoil or nuclear recoil, based on the ratio of the ionization signal to the total phonon signal. And that will allow you to discriminate against, if you're doing a nuclear recoil dark matter search, against the vast majority of events coming from electron recoil backgrounds. And so that's what I'll refer to as the low background type detectors. Now, if you look at what happens when you increase the applied electric field by a fair amount, let's say a factor of 10 or a factor of 50. Now, as the electrons and holes are moving through the crystal under the influence of an electric field, work is being done on them, and that work is comes out in the crystal again in the form of a population of phonons. So by applying an electric field, you're effectively amplifying the phonon signal in a way that is proportional to the number of electron-hole pairs, i.e. the ionization signal, and the applied voltage. So you increase your phonon signal, but the sensor's intrinsic noise is unchanged. And so what that means is you gain your signal, you're able to observe down to much lower energy depositions. So that's how you lower the detection threshold. The price you pay, however, is that your phonon signal effectively becomes dominated by the amount of ionization in your detector. And so really, you lose sensitivity to this two independent measurements, and you're not able to reject backgrounds. But as we'll see later, there are benefits for operating in both of these modes, which is why the Super CDMS Snolab experiment plans to deploy both types of these sensors. So here's a photograph of the two devices. They are in size identical, basically 10 centimeter diameter cylinders and 33 millimeters in height. You can see here in the sort of colored schematic, the sensor pattern on the top and bottom surfaces. And these are designed to allow us to extract the best fiducial volume sort of position information on the events. The detectors themselves are, roughly speaking, 1 kilogram mass, each individual one. And the idea is, well, you can see they're sitting in a nice hexagonal copper housing. So we can stack 6 of them vertically into a unit that's called a tower. And the intention is to deploy 4 of these towers in the initial Snolab payload. So we will have 2 of the low background towers and 2 of the low threshold towers with a mixture of germanium and silicon, because the different target nuclei allow you to probe, better slightly different masses of dark matter. All right, so this picture here kind of shows you how this principle works in action. And I'm gonna start on the right-hand side, the IZIPs, or the low background devices. Because you're measuring those two independent quantities, we're able to make a plot, you've seen a version of this before, of energy on one scale and this ionization yield quantity on the other. And by calibrating with sources, we can determine that this green region here, this is where nuclear recoils should appear. So that's where the nuclear recoil source, this is a 2 sigma region. And then you calibrate with electron recoil sources such as gammas or beta emitters, and you see all the colored dots. So based on the yield, the vertical parameter, we can exclude already a large fraction of those dots. In addition, because there are sensors on either side of the detector, we can measure an asymmetric charge asymmetry between the top and bottom. That gives you depth position. And so we're able to reject events near the surfaces. These are all these red events. And so you can see there are no electron recoil background in this green region, which is great. So that's a good demonstration of the discrimination ability. The problem, as you can tell, is that these bands start to flare up due to the resolution of the sensors at low energy. And really, this approach works down to 10, maybe a little bit less keV of energy. So you achieve a very good low background performance at or above the scale, which sets the mass scale that you can search for. Now, the low threshold devices, like I said, if you apply a large voltage, you get this effective amplification, and you can search down to, we have demonstrated in the previous generation device, down to a threshold of 50, roughly 50 EV electron equivalent. And you can see here X-ray emission lines in the germanium detector demonstrating that. Now, in the last couple of years, there's been a lot of interest in very light dark matter candidates. And so the logical question you can ask is, how far can you push this low threshold technology? And the answer is you can push it certainly a little bit further than this. The approach is, in principle, fairly straightforward. The low threshold technology is really, the performance is determined by the resolution, the energy resolution of the phonon sensors. And the energy resolution is proportional to the volume of the sensor, the TESs themselves. So by making the device smaller, you improve your resolution. And in fact, the last couple of years, we've built an operated detector that is roughly 1 gram of silicon. It's a square centimeter by half a centimeter thick. That's been operated a couple of times at surface facilities. So this device has a demonstrated phonon energy resolution of 3 electron volts. And when you apply, say, 100 volts to it, then you're able to distinguish individual electron hole pairs, count them at the 3% level. And what you can see in the spectrum here, this is a photograph of it on top, is the 1, 2, 3, 4 electron hole pair peaks. And so that opens the space both to look for nuclear recoils down to lower energy, but also to search for different type of interacting dark matter, such as that exhibits itself in terms of electron recoil signal. So when we put all of this information together, we can kind of construct a diagram like this that shows the overall mass range that a super CDMS detector and sort of this detector technology can probe. From the highest masses above, say, 10 GeV, the standard nuclear recoil WIMP search in low background mode, and then the high voltage devices, the low threshold, can push that down to a bit below GeV. Beyond that, the improved resolution allows you to search for electron recoil interactions, which is the point where the elastic scattering channel sort of becomes very inefficient. But below that, you can search for other types of dark matter interaction, namely direct absorption of
Tarek, are you still there? We seem to have lost you for a second there.
All right. Can you hear me now again?
Yes. Yeah.
All right. I'm going to share my screen one more time.
Go ahead.
All right. So I will just start from here, and if there's any missed material, please, I'm happy to answer any questions.
Okay, thanks.
So to enable the nuclear recall searches, especially at the lower end of the mass range, we need to know an important piece of information, which is the ionization yield for nuclear recalls at the lowest energies. This figure shows you the information we have in literature. And what we see is it's already deviating from sort of the standard theory in the field called Linhard, sort of at below a few keV. But the measurements kind of peter out at around half a keV. And what we really need to know is the value of this down to 100 eV or less. So the collaboration designed and operated a sub-experiment called IMPACT to measure nuclear recoil ionization in silicon. We went to the tunnel facility that provides us a neutron beam of 50 keVs and operated a detector with the goal of measuring the yield at energies of 100, 200, and 450 eV. This is in previously unexplored parameter space, as well as a couple of other bins, energy bins ranging from 0.75 to roughly 4 keV, which overlap existing measurements. We took data at actually several different voltages, also to allow us to probe the effect of potential effects, I should say, of the electric field on the ionization yield. So this is a simulation, by the way. Let me just say that. We want to see what is the capability of this impact measurement. And so using what we know about the detector performance and the beam parameters and stuff, we want to compare two different models. One is the standard Linhard yield. So what would we see if the yield really was Linhard all the way down, versus what would it look like if it was suppressed and following an empirical model, that we extrapolated beyond the lowest data point. And so the idea is, can we tell from our data the difference between these two curves, or even better, measure it to a very good resolution. So what I can certainly tell you at this point, the data has been taken, analysis is in progress, and we're already starting to look ahead to performing this measurement with a germanium device, and certainly both of these will be payload detectors in Snolab. All right, so let me give you a few words about the Snolab experiment. So it will be located in Sudbury, Ontario. It's at one of the deepest operating sites, 2 kilometers underground, in what was originally the SNO experiment, but now has expanded to become a multi-purpose underground facility. This is what the Super CDMS region looked like. There's one drift that's dedicated to Super CDMS. So the green cylinder is where the experiment will be. What you see here is just the shielding, the outer shielding. The detector will be in the middle. You can see the dilution refrigerator to one side and a whole bunch of operating mechanical support equipment. But to the left, I want to point your attention to the CUTE facility. So CUTE is also a dilution refrigerator facility. It can hold a single tower of the Super CDMS detectors, and it is in a large water shield. So it does not have the same low background as the full-scale experiment, but it can operate detectors and turn them around in a much faster time scale. So the two facilities are complementary to each other, and CUTE is already operating, and we have devices in it right now. All right, this is a cross-section of the experiment, but I will not dwell on this for the sake of time, but you can just see how the thermal and the shielding layers are built up around the towers. All right.
Sorry, you have about 5 minutes left in total.
Okay, wonderful. Thank you. So let me show you where we are right now and where we hope to end up in the near future. As I said, Super CDMS can look for dark matter over a very large mass range. And this is a limit plot for dark photon searches. So the blue line here is a limit that was achieved with the HVEV device I talked about earlier. And certainly the HV devices, well, they don't have exactly the same resolution as the small ones, should be able to probe in this same mass region below 100 eV, but with significantly increased sensitivity due to their much larger mass. And you can see, of course, competition from other different types of experiments. Damiket and Sensei Edelweiss are also silicon and germanium-based crystal experiments. The liquid noble xenon, and then at higher masses, also slightly different approach to the search, but sort of you probe dark photons over a large energy range. Similarly, we can look in the what I'll call the intermediate mass range for electron recoil interactions. And again, the same device, the 1 gram device I showed you, has set a limit that is, you can see here, going all the way down to roughly half an MeV. And you can see below a few MeV, again, it's the same set of approaches that the crystal-based devices, Damiket, Sensei, Edelweiss, are also able to probe down here. Whereas at above, say, 20 or 30 MeV, then liquid xenons are also able to say something significant about electron recoils. And the nice thing about this plot is we're already, in some cases, we already reached, and else we're getting very close to some benchmark theoretical models. So I can imagine us in the next few years being able to say something definitive about the nature of dark matter if it is of the electron recoil variety. And finally, going up to the top of the mass scale, nuclear recoils. Historically, this is where most of experiments have been built to look for. And so it's a very busy plot. I'm definitely not showing all of the limits there. But you can see already experiments are versatile, and they're, well, these graphs used to go to a TeV and 10 TeV, but certainly the features are sort of linear there, like the limits. And they're dominated by the liquid nobles. But you can see that we're spanning a very large range in cross-section, like 20 orders of magnitude, using different techniques looking for nuclear recoils. And at Snolab, we hope that, or plan certainly, that the CDMS experiment is going to be able to push the sensitivity from the current limits, you know, from at 1 MeV and above, down to very close to the neutron discovery limit. So hopefully this region of parameter space will be carved out. All right, so putting this all together, I'll just take the chance to make a quick advertisement. This is my last slide, is that all of these limits, by the way, the CDMS collaboration puts together in a so-called dark matter limit plotter that is available to the public. So everyone is certainly welcome to download it and play with it. And if there's any limits there that you do not find, please let me know. We'll certainly make sure to incorporate them. So, okay, this is really my last slide. So I will just conclude by saying Super CDMS Snolab is under construction. We're on plan to begin operation in late next year. And there's a large range of science that we hope to explore. Thanks.
Thank you very much, Tarek, and sorry for the technical difficulties there, everyone. Do we have a quick question? I think we have a couple of minutes. Okay, so I was actually wondering, so these IZIP detectors, the low threshold ones, is there a way that you could actually make a discovery with those detectors? I mean, to do that, I guess you would have to know the electron recoil backgrounds, or the ionization spectrum very well to be able to do that, right?
Yes. So the idea is, this line, by the way, that I showed you here is sort of a combination of the sensitivities of both the low threshold, low background detectors in silicon and germanium. And the reason we present it as a single line is because the plan is to use information from all 4 types of devices. What the low background devices will do is, because of their discrimination, give you a very good measurement of the electron recoil backgrounds in the Snolab facility, which then we can use to extrapolate to lower energies once you know what they are. And that will allow you, if you see something, that is what will allow you to make the statement, I think I'm seeing a WIMP signal versus it's just an upper limit or an unclear kind of excess.
Okay, thank you. That definitely answers the question. Let's see. I think we probably should stop there, but I'm sure people can ask questions on the Slack. We can continue the discussion. So thank you very much again, Tarek, for the very nice talk.
All right.
Thank you.
I will stop sharing.
Thanks. Okay, so now we have a short break. We're only a few minutes behind schedule, thankfully, so we will reconvene at 20 to 6, so at 5:40. Thanks, everyone. Okay, I think it's probably about time to get started again. So for all of the speakers in this session, we have 4 shorter talks, about 20 minutes each. And for everyone speaking, I'll give you 15. I'll let you know when 15 minutes have passed, and then when 17 minutes have passed. And the idea is you can leave some time at the end there for questions, or otherwise we can move things to Slack. Okay, with that, Vicente, if you would like to go ahead, if you can.
Sure, I understand you can see my screen and hear me well. Oh, perfect. So I'm going to speak about direct dark matter searches with DEEP 3600 on behalf of the DEEP collaboration. So this is us. This is the last picture that we took from the last time that we could grab a beer together while discussing physics. This is actually a subset. We are in the order of 100 researchers, a fair amount of them coming from Canada, but with also representation from Mexico, USA, and a large European representation from Germany, Italy, Poland, Russia, Spain, and the UK. And as Teresa mentioned before, like all the dark matter experiments that use argon, liquid argon as a target, or that have used liquid argon as a target in the past, we gathered together and we are part of the global argon dark matter collaboration. So let me start introducing what is the concept of the detector. And basically the idea is keeping it simple. So we don't use combinations of energy release channels, but we only use the scintillation. We have a single phase liquid argon detector. And as you might know by now after Teresa's talk, the noble elements scintillate, and the excitation that produces this scintillation comes mainly from 2 states in the noble elements dimers. So we have the singlet state that decays fast in the order of nanoseconds. And this state is dominantly populated by nuclear recoils, producing a signal like this one that you see here, in which a fair amount of the light that is collected within the first microseconds since the event is within actually the first nanoseconds. The gate that we use for calling this light prompt is 60 nanoseconds. While there's also the triplet state that decays more slowly, in the case of argon in the order of 1.6 microseconds. And this state is dominantly populated by electronic recoils, producing a signal like this. So if one does the ratio between the prompt light with respect to the total light, this is what we call F prompt. And it gives you basically the ability to discriminate between different kinds of particles. Here we have what we call the nuclear recoil band at high F prompt, and here at the bottom we have the electron recoil band at low F prompt. So with these, basically the dominant backgrounds that we have in this kind of experiments that are electromagnetic backgrounds, especially in argon experiments that we have argon 39 decay, that it is a beta decay and hence producing an electronic recoil. We can discriminate against that just using this variable. In addition to that, having a detector that has enough granularity with a big enough number of photon sensors around the volume, we are able to perform position reconstruction with a precision in the order of the centimeters. And because of that, we are able to fiducialize. That is, taking out of the analysis all the events that actually produce a recoil in the outer shell of the sphere, and that are likely to come from external backgrounds or from the surface itself. So this is the concept, and this is what how this concept is materialized in our case. This is DEEP 3600 with 3.3 tons of liquid argon inside the target. And this is contained by an ultra-clean acrylic vessel with 85 centimeters in radius. Now, argon scintillates at 128 nanometers, which is not visible for commercial PMTs. And what we do is we evaporate TPB in the inner surface of this acrylic so that this light is converted to visible light. Now, these PMTs also are not the cleanest thing in the world, and it's not something that you want to have very close to your target. So we keep them away while not losing light using light guides. These are acrylic light guides that the photons that arrive here are guided through them towards the PMTs, and then we gain distance, which is the best thing that you can do against anything that is emitting background. And in particular, it also, together with all these layers that you see here, that are in essence plastic layers that are good for thermalizing and absorbing neutrons. So we keep away neutrons from our external neutrons from our target. The number of PMTs that we have is 255, and because of this relatively simple configuration, we have a large coverage of the surface of the detector, 75% coverage. And this thing is all inside a water tank that is instrumented with these outward-looking PMTs that you see here, in order to veto the muons using the Cherenkov light that the muons produce in the water in the tank. And the whole thing is located 2 kilometers underground at Snolab. We are neighbors to the colleagues in the previous talk. So backgrounds, we published a detailed characterization of our electromagnetic backgrounds back in 2019, in which here you can see the large amount of contributions that are playing a role here in the electromagnetic background. The one that is more highlightable probably is the argon, the presence of argon 42. I just received a message that participants can now see my screen. I hope you were seeing my screen before.
We were certainly seeing your screen before.
Okay.
I think you can ignore that.
Okay. So we have argon 42, and which is has a significant contribution from nuclear tests back in the day. Besides the electromagnetic backgrounds that we can, as I mentioned before, discriminate with our F-Brown variable, Gaussian discrimination, we have the usual alpha backgrounds, radon daughters, and the alpha emitters in the inner surface. These backgrounds in our case are well understood and are subdominant for our WIMP searches. And here you see that everything is below the microbecquerel per kilogram and even to the nanobecquerel per kilogram level. Regarding the irreducible neutron background, it is well predicted in the control regions that we defined in the surroundings of our region of interest. And we expected, and spoiler, we didn't see any event in the region of interest. But what is worth start highlighting here is the fact that the number of events in our region of interest is not dominated by any of the usual culprits, but instead is dominated by alphas from the neck that I will describe in a couple of slides. So this is the result that we published in 2019 regarding WIMP searches. We observed 0 backgrounds, and we have the leading exclusion with liquid argon targets. We have excellent control over the main background types, and the sensitivity is limited by this topologically induced background. And since then, we've been taking data stably until March 2020, where the pandemics kicked in and it was difficult to maintain operation underground, and we decided to leave the liquid argon evaporate. And I'm not going to detail here because I'm going to describe this starting here. So what is this background that is becoming a nightmare for us? So in essence, we have, so this is the main part of the detector, and on top of it, we have what we call the neck. And here we have the acrylic flow guides. This is a zoom of this area. And on top of them, we have the cooling coil. So what actually is happening is that we have quite clean acrylic surfaces here, but these few events that are produced here, and because of the cooling coil being on top, there is liquid argon flowing down and being condensated in these surfaces. Oops, sorry. So the alphas that are produced here, they scintillate in the thin film of argon that is deposited on top, and they produce light that can be seen in the detector. Now, this light should be identified by the position reconstructing algorithms like out of the fiducial volume, like very far up in the detector. And the alpha energies are much higher than the energy recall, the recall energies that we expect. So it should be out of the region of interest, both in terms of Z and in terms of energy. Now, what happens is that because of this particular shape, you can see that out of the light that is produced, imagine that the light is emitted in 4 pi, but only a small proportion of it will be produced within the cone that can actually reach the PMTs in the detector. So there is a small proportion of all the light that we can see, and this shifts the reconstructed energy towards lower energy. Plus, because of this kind of cone shape that points towards the bottom of the detector, the event is reconstructed lower down in Z. So we have these two things that happen simultaneously and that push our events towards the region of interest. This is in a big data set that has been simulated how the distribution of events in this parameter space Z versus energy would look like. And this is how our data looks like, which is behaving remarkably. Just to highlight that the Monte Carlo is behaving remarkably well, and that we actually understand what's going on over there. Now, we understand it in average, but we want to discriminate against it event by event, and that is where the difficult things come in. So in addition to the neck alphas, we have dust alphas, and this is, so we have evidence for presence of dust particulates in the liquid argon. And now, in these particulates, as everything else in the world, have a small proportion of thorium and uranium. When these decay, thorium, uranium, or their progeny, when these decay, they produce alphas that a part of this energy will be released inside the dust and will not scintillate, while the rest of the energy will be released in the liquid argon and will scintillate. So this, again, pushes the energy that we see towards the low energy side and pushes those events that should be at high energy inside the region of interest. Now, we have identified the problems. What are we going to do, or what are we doing in order to solve it? So we are using both software and hardware approaches. In the software plane, we are using machine learning with 3 different approaches: random forest, boosted decision trees, and neural networks. The first 2 use high-level variables like energy, reconstructed position, and so on. And the latter uses quite low-level information. So just the charge in each PMT, which is proportional to the number of photons seen by each PMT, and the arrival time of the first photon to each PMT, which ends up being, could be used as an indication of the position as well. So the data sets are produced with Monte Carlo. We have a full Monte Carlo of the detector response, and we only select the events for this training that pass all the analysis caps, both for NEC events and for nuclear recalls on Argon 40. And in the case of the NEC, that is the one that we've been exploring for longer and which we have better results so far. The gain is twofold, with an enhanced signal acceptance, more than twice larger than CAT-based analysis, and the leakage of background events. We have a rejection of 99% in the CAT-based analysis and 99.9% here. So the leakage is a factor 10 less. Here I show the performance of one of the classifiers. Blue are nuclear recoils, orange are NEC alphas, and how the neural network performs, and how if one selects different thresholds here, different scores as good or bad events, how the signal acceptance evolves with the background rejection. Of course, in order to validate all this, we've gone through thorough benchmarking and internal validation process within the collaboration. And basically, one of the most important steps is making sure that the classifier that we are training with Monte Carlo is applicable to data. And in order to do that, we use Argon 39. So this is not trained for Argon 39, but what we know is that whatever we apply the algorithm on, it has to behave similarly for Monte Carlo and data. And this is the result of that, which is remarkably good. And the same we have in progress for the dust problem.
Sorry, just to say you have about 5 minutes of the total time left.
Okay, so I will skip this one. And I will go to the hardware upgrades. We are performing 2 hardware upgrades. One of them is covering the inner, well, all these layers that from which the NEC alphas are produced with slow wavelength shifter. With that, the first thing that we have is, since it's slow, a certain amount of the light will be produced later in time, and then these things will be pushed out of the region of interest towards lower F prompt. And we will also have a better light collection, because the things that are emitted upwards, they can, after the light conversion, they can be emitted downwards. So overall, we are pushing the events out of the region of interest because of higher energy and because of lower F prompt. And we are also installing an alternate cooling system in which the cooling will not happen here, and we will have less condensation in the flow guides. And also we will be taking the liquid argon from the bottom of the detector, and we can filtrate the dust particulates out. Because so currently all the operation that we've had so far has been without recirculation of the liquid argon. In parallel with this, we've performed other physics searches, and for instance, the Planck scale mass multiscattering dark matter. Basically, dark matter, heavy particle in the order of 10 to the 12 GeV, and with a cross section to interact with nucleons of 10 to the minus 25 square centimeters, would produce a signal that is like several interactions through the detector. If you model that response of the detector, you would expect a signal like this, and we've performed a blind analysis to see what we see in this region of interest. It is completely separate from the WIMP search region of interest, and we've freshly submitted these to PRL, and we have new limits of unpopulated parameter space so far. We have also reinterpreted the WIMP search that I showed before within a more general non-relativistic effective field theory framework, in which isospin violating interaction is considered, for instance. And here we see in that case how how the sensitivity of DEEP 3600, for instance, would be leading against xenon experiments. And more important than who is leading, the message that I think that is nice to convey here is that the use of several different targets is important in order to understand the properties of the WIMPs. And besides that, we also explored the effect of possible halo substructures like the ones observed in Gaia, and in these constraints. So going beyond the standard halo model that we all know that is the best thing that can be used while nobody likes it.
You have a couple of minutes left. Sorry. Yeah, go ahead.
No problem. So I'm finishing this. So conclusions and outlook: we have excellent control over Argon 39, neutron, radon, and surface backgrounds. Several new physics searches performed on the already collected data set. Currently, our sensitivity is limited by NEC and dust alpha backgrounds, and we are performing multivariate analysis to recover this sensitivity together with the hardware upgrades that I mentioned that should be ready by the end of spring 2022. And we have a bunch of upcoming papers on solar neutrino absorption measurements, dark matter results with this multivariate analysis, and the specific activity of Argon 39, and technical papers, for instance, like in the slow wavelength shifted coherence. And that's all from my side. Thanks so much for your attention.
Thank you very much, Vicente. We have a couple of minutes, I think. If anyone has a quick question, feel free to raise your hand or type in the chat. So I have a question actually on this multi-scattering dark matter.
Mm-hmm.
There was a region that was marked as extrapolated. Can you explain what the difference is between the deep 3600 region and then the extrapolated region?
Yeah, so the extrapolated region is a region in which we do not have a simulation because it would be too computationally expensive, but in which we have assumed very conservative assumptions. So in principle, so it is extrapolated, and you see that the edges are quite square. Just, but yeah, the reason for that to be quoted separately is because of that. Okay,
it's a very cool, very nice analysis. It's a very unusual thing to look for, but it's very fun.
Yeah. I mean, the question is why not? Why not look into this if you have the data there?
Yeah. Okay, I think we should probably move on, but thank you very much again, Vicente. We can, if anyone has any more questions, I'm sure they can go on Slack, and hopefully Vicente has some time to answer.
Definitely, thanks.
Okay, so we can then move on to Luca Pagani. If you want to share your screen.
Yes, I hope everybody can see my screen.
Yes, I can see it perfectly fine. Go ahead whenever you're ready.
Okay, so hi everybody. My name is Luca Pagani, and today I will give you a talk about DarkSide 20K, and in particular of its K feature, and also about what's the future for the liquid argon dark matter detectors. So as you can see from the plot here, the main goal of DarkSide 20K is to try to search for high mass WIMPs. In fact, here you can see the projected sensitivity for this experiment. As you can see, they are reaching towards this gray area, which is the neutrino floor. And basically, this gray area indicates that your detector, if you have a sensitivity at that level, your detector will be dominated by neutrino events and not by dark matter. So how DarkSide wants to achieve this sensitivity? Basically, the idea is to have a background-free exposure of 200 tons per year. And what I will tell you after this slide are the key feature and the key technology that are needed to do that. So the first key feature is basically location and the design of the detector. In particular, DarkSide will be housed at the Laboratorio Nazionale del Gran Sasso, and its design can be seen here in these two cartoons. Following the good design of DarkSide 20K and DarkSide 50, basically DarkSide 20K will have a Matryoshka-like design. From inward to outward, we have the Two-Phase Tpc, which feature low radioactive argon. After that, we will have neutron veto composed of a passive gadolinium loaded acrylic sandwich between two active atmospheric argon buffer. After that, there will be a Faraday cage, which isolate the detector both optically and electrically. And then we will have a passive atmospheric argon layer until we reach the membrane cryostat, which is a protodune-like one. So the second feature, as I was saying before, is having a radio pure target. In fact, Darkset 20K will use low radioactive argon extracted from the mantle of the Earth. And since it's coming from underground, we call it underground argon. So this argon will be extracted by the Urania facility at a rate of 330 kilograms per day. Why we want to use underground argon is because basically it has a low content of argon-39, and in Darkset 50 we measure a factor of 1400 in reduction, in depletion of argon-39. So once this argon will be extracted by Urania in Colorado, it will be shipped in high pressure gas cylinder by ground and sea to the area facility in Sardinia. We will ship it by ground or sea because we want to limit the activation of the argon. As I was saying, the argon, after will be extracted, will be purified by the area facility. The area facility is a 350-meter tall cryogenic column in Sardinia, which can purify the argon at a speed of 1 ton per day, which can produce in a timely fashion all the argon needed for DarkSide. It also has an option of performing isotopic separation of argon 40 versus argon 39, but this is a slower rate. As you can see from the picture here on the right, a prototype of the area column was installed at surface, and its performances were studied using nitrogen, and they agreed with the expectation. And also the first area module was installed in April 2021. So we produced the argon, we purify it, we had to check if our purification is working fine. And this will be done with the DART facility at Canfranc. DART is let's say you can see a nice picture of this single phase liquid argon detector featuring 2 silicon PMs. Will be able to measure a depletion factor of around 1000 with a 10% sensitivity. A lot of work is going on with DART. Its performances were validated in April 2021, and also is foreseen installation in the RDM detector by 2022. Not only we have to produce argon that is radio pure, we have to keep in that mode, still radio pure, and for this we design a cryogenic system. This was done at CERN, and here you can see a nice picture of the all cryogenic and handling system for argon at CERN. Tests were done like I think a couple of months ago that showed that good behavior of the system. Tests are also foreseen to test the system on standard 1000 standard liter per minute, which is required by the Darkset 20K to keep an electron lifetime of 5 milliseconds. Another key feature to achieve our IMAS WIMP search is the TPC itself. So we are using a dual phase TPC, which relies on detecting both primary scintillation that we call S1, which is related to the scintillation signal, and a delayed signal called S2, which is related to the ionization produced. In Darkset 20K, the TPC will be made of pure acrylic, and the volume will be, and the fiducial volume will be defined by the top and bottom acrylic window plus a reflector cage made of reflective foils where TPB will be coated. Also, to function as a TPC, both the top and bottom window will be coated with a conductive transparent polymer called clavius, together with the fact that the walls will be grooved in such a way to resemble some field shaping ring, and also those rings will be coated by clavius. There is also the only thing that is not acrylic or clavius or TPB inside the TPC will be a stainless steel grid that is used to separate liquid from the gas. Another key feature to achieve the goal of DarkSide-20K are the photon detectors too. DarkSide-20K will use silicon PMs, and here I just want to show you a list of all the benefits that silicon PMs can provide with respect of PMT. Just to mention a couple, they have a higher photon detection efficiency and a better single photo resolution, all of these while having a lower biasing voltage. Also, silicon PMs can be ganged together to form large area photodetector units. And here on the right, you can see an example of a silicon PM that will be used in DarkSide-20K, which has an integrated front-end electronics. So timeline-wise, all the silicon PM for DarkSide-20K will be produced in a industrial grade foundry. Then they will be assembled and packaged at the NOAA facility in nearby Gran Sasso, and then they will be shipped in Naples, where they will be tested. So in a more schematic way, these show you how the silicon PM will look like in DarkSide-20K. So from top left, you have the silicon PM that will become a photon detection module, 5x5. Those photo detection modules can be assembled again together in a bigger unit called a photon detection unit or motherboard, which will have both steering module and the optical transmitter. Those motherboards there will be used to cover the octagonal shape that constitute both the top and the bottom window. And those silicon PM array will be just installed on top of the both of the fiducial volume. So now let me change a little bit the gears and let me tell you what's the R&D that is going on for DarkSide-20K. Here on the left, you can see a drawing of what I can call the proto detector for DarkSide-20K, which is called Proto-0. This detector will feature two motherboards, and they will be tested in Naples, and it will be used to optimize the S2 signal. After this Proto-0, there will be DarkSide Proto, which will be operated with atmospheric argon at surface, and it will be used to validate all the detector components, maybe the same that will be used in DarkSide-20K, the same size that will be used in DarkSide-20K. It will be used to validate the photosensor and also to perform additional tests on the cryogenic system. Just to show you that something is going on, here are some pictures of the R&D that is already accomplished at various universities. So also, a lot of work is going on concerning the VITO. Let me just remind you how the VITO will work in DarkSide-20K. So the neutrons will be moderated by the acrylic, and then they will be captured by this passive gadolinium-loaded acrylic. The gadolinium will emit multiple gammas with a Q value of about 8 MeV. And basically, those gamma will interact with the argon in the buffer, which is viewed by silicon PMs The veto is divided in 8 azimuthal segments, and those are optically blind to each other, and these will be used to maximize the collection efficiency and also to reduce the possibility of Argon-39 pileup in the veto. Just to tell you, here on the bottom right, you can see a picture of a piece of acrylic with gadolinium loaded that was made in China, and the results are promising about this R&D. In summary, concerning DarkSide-20K, those are the way that we want to minimize our background. I would say that it's important to mention that we are using dual-phase TPC, which rely on the detection of both of calorimetry on both of S1 and S2, because the ratio between these two signals depends on the type of the particle. Not only that, but also the shape of S1 is particle dependent. And as Vicente already said in the previous talk, using PSD, they achieve a very promising background rejection. To understand it, you can see both Vicente talked before, or you can see that electron recoil and nuclear recoilers, they have a very different shape from the two waveform here on the bottom. Last but not least, also the fact that we will have an active veto, so we can use the anti-coincidence between the two detectors. So this said, what is the budget, the background budget for DarkSide-20K? This table summarizes everything, and this table was done considering a 200 ton year exposure for the fiducial volume of the TPC, which is 20.2 tons. After we apply all the TPC and the veto cut, plus restricting our energy region of interest in the 20 to 200 kV region. As you can see, basically we are dominated by the neutrino-induced nuclear recoil because they comprises the most of the background. So to recap, DarkSide-20K is planning to 10 years long search for high dark matter. And the idea is to operate the detector with less than 0.1 background events. In this way, we will be able to approach the neutrino floor. One thing to remind you and to note is that all these exclusion plots are done only considering a factor of 1400 in the depletion of Argon-39 for underground argon. As I was mentioning before, there is still a little bit room of improvement because of the isotopic separation. So
sorry, just to you have about 4 minutes left from the total time.
I'm last slide next.
Perfect.
So now, lastly, let me just spend a couple of words telling you what the future will look like for the global Argon dark matter community. So as I was saying, DarkSide will be done at the LNGS. Next will be Argo, and both will be try to reach the neutrino floor. Not only that, but also try to see core collapsing supernova neutrinos. At this point, Argo is still in the conceptual stage. It will feature 3,000 tons per year of argon exposure. And as a side, it will also be able to precisely measure the solar neutrino spectrum. These, both dark side 20K and Argon, are for high mass WIMP. The collaboration is also working and developing a detector specifically designed for low mass search, and with a lot of imagination, we call it dark side low mass. And basically, that's it for timeline and future. So I just want to conclude showing you the dark side collaboration, and if you have any question, I'm here to ask, to answer. Sorry.
Thank you very much, Luca. Thank you. Go ahead, Teresa.
Yeah, thanks for the talk. I have a question to your silicon PMs. Because you, if I saw it right, you mentioned that they had like 200 hertz dark count, and you have, of course, lots of them around. So I was wondering, what is the role that they play on accidental coincidences, or maybe at which energy threshold the accidental coincidence play a role? Because I guess at some point you have so many dark count rates that they would contribute.
So the way to mitigate this is how you gang them together. And let's say so far we did a simulation trying to implement this dark count rate, but we didn't find any problem concerning threshold effect or saturation effect. Even if trying to simulate both the highest background we can expect naturally, which is thallium, neither if we are trying to simulate neutron events. So I guess, let's say the signal to noise ratio is good enough that this is not a problem.
Okay, so do you think they won't be contributing to accidental coincidences that contribute to the dark matter region?
Yeah, let's say I'm not a super expert on silicon PM. I completely work on something different, but that's what
okay,
I
thank
think.
you. Thank you.
Okay. Do we have any other very urgent or very short questions? Otherwise, I think if anyone has any more questions, they can ask in the Slack. Hopefully, Luca has some time to answer. And we can thank Luca again. Thank you very much for the very nice talk. And then it's time to move on to Michelangelo. We have Michelangelo around. There we go.
Yes.
To talk about.
Let me. Oh, sorry. Please go ahead.
No, it's just. I was just introducing you. Yes. So we have Michelangelo talking about Damiket. So you have about 20 minutes. Please go ahead whenever you're ready.
All right. So hello, everyone. So this presentation is, I'm going to tell you about the latest results and development of the Damiket experiments. And so to do so, at first, I will tell you about Damiket Snolab, and in particular, how we deal with backgrounds, and also detail the construction of the first comprehensive CCD background model, which we then use to perform our latest WIMP search. Then I will switch to Damiket Modan, which is the upcoming dark matter in CCD experiment. And so I will introduce you to this new technology we are about to deploy, the Skipper CCDs. And then again, talk about how we are dealing with the backgrounds, and also mention the deployment of the Damiket prototype experiment, the low background chamber. All right, let's start. Okay, so Damiket Snolab has been active since 2011 as a collaboration, and the setup is at Snolab beneath 2 kilometers of granite. Very essentially, you can see it in these pictures over here. It consists of an 8 CCD tower in a copper cryostat, which is enclosed in lead and polyethylene shielding. So why do we use charge coupled devices? It is because they are outstanding devices sensitive to a few charge carriers, and they also have very good spatial reconstruction and particle discrimination capabilities. The catch is that for dark matter, we need to maximize the exposure. And so our CCDs are much thicker than the usual astronomical CCD. And in these conditions, we can essentially look for two dark matter candidates. Sorry, not two, but two typologies of dark matter candidates, WIMPs through nuclear coherent scatterings, and hidden sector candidates through electronic interactions. So let's now dive a bit into the workings of CCDs. So CCDs are arrays of silicon pixels, and when radiation crosses them, it produces electron-hole pairs, which drift in the direction of the electric field and are collected at the buried channel, less than a micrometer below the surface electrodes. And while these charge carrier drifts, they also diffuse laterally, and this is the trick we use to essentially quantify the vertical coordinate of interaction. So, in particular, we measure for that the lateral spread of the cluster, which we label sigma. And this is an important quantity in our analysis, as you will see later. So once the charge is collected, it can then be transferred to the readout amplifiers in the corner of the CCD. And this is done through in-phase voltages called clocks. And we have very good performance in terms of charge transfer, we lose less than a carrier in a million per transfer. Then we have a readout noise of about 1.6 electrons, and our dark current is less than 1,000th of an electron per pixel per day. Let's now shift the focus a bit to backgrounds. So essentially, as any dark matter experiment, our sensitivity is limited by the overall background rate. And as most experiments, we do operate underground to mitigate our backgrounds, and then select the material carefully and assay it for radioactivity, and then also optimize our shielding. After that, we still have residual backgrounds, and we want to essentially discriminate and quantify them if possible in order to build like an accurate background model. So here I'm reporting the results of the background model construction of Damiket Snolab. And what you can see is how important a part in CCD contaminants play. And so luckily, I could say CCDs have a unique capability that allow us to quantify the backgrounds that are in the sensor themselves. And yeah, so let me tell you a bit more about this capability. So the major contaminants in the CCD themselves are on the surface, both of the CCD and of the sensor, so the sort of the active region. And this would be lead-210, which stems from radon deposition on the CCD. And then we have also bulk contaminants in the active region, and those would be silicon-32 traces, but also tritium from activation. And so essentially with CCDs, we can quantify those isotopes that are at the top of a decay chain to this spatial coincidence analysis technique, which essentially consists in observing decays that are spatially coincident and whose energies and time separation is compatible with those expected for a given decay chain. And this is essentially how we are able to measure, for example, silicon-32 or set a limit on lead-210 And this information is very important for the construction of the background model. You can see here 2 examples of spatially coincident clusters for silicon-32 and lead-210. So yeah, this information is very important for the construction of the background model, and we use it with the aid of Gent4 simulations to construct it. In particular, we perform over 1,000 isotope volume combinations. We perform simulations over 1,000 combinations of isotope and volumes. And then to this, we apply the CCD response and then cluster the output in a and so we build a 2-dimensional distribution in energy and sigma, which I remind you is essentially the depth of the interaction. And so after that, what we do essentially is a 2-dimensional bin likelihood fit in a region which we're not very competitive to look for dark matter essentially, and that will be above 6 kilo electron volts, and then we just extrapolate the model that we get from this fit in the region of interest below 6 kilo electron volts. So what you can see here is the projections essentially of the background model and some of the components that it consists of. And yeah, so essentially we use these results to perform a profile likelihood ratio hypothesis test. We use this background model on an 11 kilogram day exposure data set, whose result is reported in this plot here. Essentially, you have our data in blue and the background model in gray. And so what we have is that above 200 electron volts, the data, the background model is consistent with the data. And however, below 200 electron volts, the fit prefers an exponential bulk excess that yeah, so the fit prefers this exponential bulk excess that we sorry, yes, that it consists of about 17 events and is driven also by events at low energies and sorry, at low sigmas. And so we do not provide a definite interpretation from this for this access. It could be very well a missing front component in our background model, since it's driven by these events at the low sigmas. And I remind you that low sigma correspond to front sort of shallow depth in the CCD, while high sigma correspond to deep sort of events in the CCD, deep interactions. Or it could also be an unaccounted detector frontside effect, but also possibly new physics. Here I also report the energy projection of the access and the probability distribution of the possible signal number of events and decay constant of the exponential function model in the access. So we have done our due diligence concerning possible systematic sources of uncertainty. We have checked that this excess does not stem from a gross mismodeling of front surface events. And to do that, we have essentially removed all single pixel events from our data set, which are representative of the front category, and reperformed the hypothesis test with this data. And this was essentially compatible with the result that we had with the full data set. Then we have also verified our fitting machinery and performed parallel analysis with other techniques. And notably, also verified that the access is not compatible with the background fluctuation, and that it is by far the most significant access in our data set. So despite the access, we are able to set limits on the WIMP, the spin-independent WIMP nucleon scattering cross-section. At high values of mass, we reach our projected sensitivity, but that is not the case at low values. You can see the discrepancy between the red line and the red band, the red line and the red band. However, despite this, we're still able to set the, to date, strongest limits from a silicon target experiment below 9 giga-electron volts. So that was how much I wanted to tell you about Damiket Snolab. Now we can talk about Damiket Modan, which is the future dark matter in CCD experiment. And this will be deployed in the Modan underground laboratory in France. And so the novelties with respect to Damiket Snolab are that we are going to have a sub-electron resolution. And so we are actually going to be able to count the electrons in each of our pixels. And that will give us essentially a threshold of about 1 electron volt, for which we are also developing ad hoc electronics for noise optimization. And then, of course, there is probably the most ambitious of our goals to suppress the background rate by 2 orders of magnitude with respect to Damiket Snolab. And so what's coming next is the deployment of a prototype low background chamber, which has intermediate goals with respect to Damiket Modan. But the actual kilogram scale experiment is probably going to take place starting from 2023. And so in this slide, I also report the current design of the experiment, although this is still subject to variations, and the WIMP cross-section sensitivity plot, where you can see that we are rather competitive. So let me just tell you quickly about these Keeper CCDs. Essentially, they differ from sort of ordinary CCDs in that they have a floating gate that allow to do non-destructive, multiple non-destructive charge measurements. And so doing that, we can essentially measure the charge in a pixel several times, and then we average the pixel value. And this is essentially the trick that we use to get single electron resolution, which in practice means resolving single electrons. You can see here how increasing the number of non-destructive charge measurements gives and gets us eventually to having single electron resolution. And that in a fashion dropping by the square root of n, where n is the number of non-destructive charge measurements. So now let's focus a bit more on backgrounds. So from Damiket Snolab, what we saw was that we had like more than half our contaminants in the CCDs, then the rest was in copper and the mixed material contribution. So addressing the in-CCD contaminants, what we have learned from Snolab is essentially to improve our storage and transportation protocols. And that will address mainly tritium, which stems from activation and lead-210. Then for 32 silicon 32 traces, we still are we're still gonna use our spatial coincidence analysis and reject it. As for copper,
Sorry to interrupt. You have about 5 minutes left in the total time.
Sounds good. Thank you. For copper, we have activation again, but also lead-210. And so the idea is here to use electroformed copper with minimized activation time. And these sort of solutions will drastically reduce these two backgrounds. And so what's left is about 2 DRU from this mixed material contribution. And here we're working hard also in the context of the low background chamber of Damiket for the design, the material selection, and also possibly fiducial cuts that can essentially get us to achieve the Damiket desired low backgrounds. And so let me tell you just a bit more about this low background chamber. This is the Damiket prototype detector, and it will already deploy skipper CCDs, which means that we will have a threshold of the order of the electron volt. And this will allow us to extend the Damiket background model down to single electron signal. And then it has an intermediate background goal with respect to Damiket Snolab and Damiket, so that would be 1 DRU. And we are well on our way to this goal. So at the moment, with the current design, our simulations predict the background overall of about 5 DRU, with the major contributor being essentially these copper supports of the CCDs. But here we know that going from OFC to electroformed copper, we are able to reduce these considerably. And then also we are there is an ongoing design of the cable that transport the signal and the clocks for the CCD to reduce its radioactivity. And so if we can also use fiducial cuts. So the bottom line is that the 1 DRU goal is within reach with the LBC. And so this is as much as I wanted to say about the Damiket experiments. So to summarize, for Damiket Snolab, we have performed a WIM search on an 11 kilogram day exposure data set. And this is detailed in this PRL publication. To do that, we have studied our background thoroughly. And for example, the results of our spatial coincidence analysis have been published on GINST. And then in general, the construction of the background model was a huge effort by the collaboration, and we are in the process of internally reviewing a very long, detailed technical paper that's detailing it, and this will be submitted to PRD soon. Yeah, something I didn't mention, but is very important, is that also Damiket Snolab will upgrade its setup, and we will use skipper CCDs. And so essentially we will be able to better investigate the excess that we observed, because we will have a much better event reconstruction at low energies. As for Damiket Modan, I told you that Damiket Modan is a kilogram scale skipper CCD detector that's striving for 0.1 DRU background rates. To do that, we are about to deploy a prototype 1 DRU chamber, the LBC, that will give its first science results in 2022. And in the meantime, the research and development of Damiket continues, and probably the detector will be installed in 2023. And so this is as much as I wanted to tell you. I leave you with the sensitivity projections for Damiket for its different dark matter candidates. And it was a pleasure to give this talk. So thanks a lot for your attention.
Thank you very much, Michelangelo. Do we have perhaps a quick question? We maybe have 1 minute before we have to move on. Well, I actually have a question about this intriguing excess. So you said that these are the strongest limits from a silicon detector at these masses. Is that true?
Yeah, as far as I know, below 9 gigaelectron volts.
Okay, so if you wanted this to be new physics, which was dark matter nucleon scattering, then you would have to you would have to really focus on scattering in silicon, but not, for example, scattering in, I guess, argon or xenon.
Right.
Right.
I mean, yeah, I mean, that's a very good point. Yeah, I mean, there is, I think, some physics that points to, different material possibly responding differently to dark matter, like isospin violation and this kind of stuff. But indeed, it is a good point, and for example, noble liquid experiments, or noble liquid experiments have set limits in this region which are stronger than what we are doing. So, but yeah, that is the status, and we will definitely investigate this further with the Damiket Snolab upgrade.
Okay, thank you very much for telling us about this very interesting. Well, all of these interesting results. I think we have to move on, so we can thank Michelangelo again, and we move on to the final talk of the afternoon. Nicolas Avalos, if you're here.
Hello.
Hi.
Hopefully you can hear me and see my screen.
I can hear you. You have about 20 minutes. Please go ahead whenever you're ready.
Perfect. Well, first of all, I would like to thank the organizers for this opportunity to present our experiment in this conference. My name is Nicolas, and I'm talking on behalf of the DM2 collaboration. We are running an experiment to detect directly dark matter in Argentina, South America, specifically in the city of Bariloche. And the way in which we are looking for this dark matter signal is by the search of a daily modulation of events and using a Skipper CCD detector. So first of all, let me tell you about this diurnal modulation that we are looking for. We need first two assumptions in order to see this diurnal modulation. First of all, that there is a dark matter wind. This is an assumption that a lot of experiments already have. There is a net flux of dark matter particles that come from the direction of Cygnus. And the second assumption is that these dark matter particles should interact with nuclei inside the Earth. Therefore, they have a possibility to scatter away before reaching our detector and generate a difference in the event rate that we see between a certain time of the day and 12 hours later. So to illustrate this last point, we are located here at 41 degrees south in Bariloche. No? And the dark matter wind comes from 40 degrees north. So at some point of the day, we will have Cygnus barely above the horizon, and the dark matter particles will only have to get across the atmosphere to reach our detector. And therefore, we would expect a maximum rate of events. But 12 hours later, the dark matter wind will come from below us, and it has to get through the whole Earth, and therefore we'll have many opportunities to scatter away before reaching our detector. So we would expect a minimum in the rate of events at that point of the day. And also, I would like to say that this modulation is distinguishable from a solar day modulation, because if at some point of the year, for example, in September, we would have a maximum flux at midnight, then as the Earth travels around the sun, 6 months later, this maximum flux of events should happen at midday. So if we happen to see a modulation that has the correct phase at some point of the year, then all we have to do is wait 6 months and see if this modulation has drifted its phase. So I will now very quickly talk about the detector, because it's the same type of detector that they use in Damiket and that has already been very nicely presented. So we use charge-coupled devices and specifically a Skipper CCD. The scientific charge-coupled device consists of a silicon bulk. There is a two-dimensional array of pixels in its surface. Any incoming particle that interacts in the silicon bulk generates electron-hole pairs, and these holes will drift towards the surface because of an electric field, and they will get caught in this pixel structure that is in the surface of the CCD. So there, the charges drift towards a potential well, and after that, they can be trapped in these potential wells until we perform the readout. This readout occurs by moving the charge from one pixel to the next and towards a sense node. In this sense node, the charge is translated into voltage, and then we can translate this voltage into image, into colors for an image. So we obtain images like this one, in which we can distinguish these different particle tracks, for example, muons, electrons, and also point-like events, which may be because of alphas, neutrons, X-rays, or WIMPs, if that's the case. So these regular CCDs have some readout noise that perhaps will allow for a low energy threshold of about around 50 electron volts. But as already has been said in the previous talk, this can be lowered, and this can be lowered by using skipper CCDs. So the readout stage in these skipper CCDs has been changed in order to allow each pixel, the charge of each pixel several times and without being distracted. So now we can reduce the total readout noise by the square root of the times we read the charge. And we can read enough times in order to have a readout noise below the single electron resolution. Well, this is an illustration. If with only one readout per pixel, we have all this noise. But when we read a lot of times the same pixel, we can be able to separate the pixels that have no charge at all from the pixels which have only one electron, two electrons, and so on. So now we have lowered the detection threshold down to the silicon band gap, which is about around 1.2 electron volts. Now I will talk about our experiment itself. This is our detector. It's a prototype skipper CCD. We have around 100 milligrams of detection mass. We have this active region of about 1 × 2 centimeters of size. We have around 1 megapixel. This is 200 micrometers of thickness. And we have 4 readout amplifiers, one on each corner of the active region, which allows us to read each quarter of the CCD in parallel. Now, this is inside a copper housing, which is inside a vacuum chamber. Now, we need this vacuum chamber so that we can have the CCD in a cold temperature without having the air condensating around it. And the way in which we lower the temperature of the CCD is by a thermal coupling, by a cold finger, which is a copper cylinder, which is in direct thermal contact with liquid nitrogen. So the liquid nitrogen is at 77 Kelvin, and this coupling allows us to have the skipper CCD at around 100 Kelvin of temperature, which is a nice working temperature to reduce the thermal noise. So with these CCDs, what we have as data are images. But first we have to process these images in order to have the needed data for the physics. So first of all, we need to average the skipper samples. Each time we read a pixel, this value is stored in a different in an array, and we need to average each of the samples in order to obtain the final image. Then we need to know where the zero is in our image. So we use a region called the overscan, which has pixels that haven't been exposed. And so in that way, we will know where is the zero of our image. We also have crosstalk, which is any time that we have a positive signal in one of the amplifiers. In every other amplifier, we see a fake negative signal. So we can apply a correction to this. We do it. Then we need to calibrate the image. We have arbitrary units for the charge at each pixel. But we know that there are different populations of pixels that have 0, 1, 2 electrons. So we fit these Gaussians to each of these populations. And when we subtract the mean of the Gaussian as the 1 electron pixels minus the 0 electron pixels, we know what is the gain of each of the amplifiers, then divide the value of each pixel by the gain and obtain the final value in electrons for each pixel of the image. As you can see here, we cannot perfectly well distinguish the 0 electron pixels from the 1 electron pixel in this region. But that is because we have a slight correlated noise in each of the amplifiers. So we have developed an algorithm that allows us to separate the events that have 0 electrons from the one that have 1 electrons using a machine learning technique called clustering. And now we can perfectly know which pixels have 0 electrons, 1 electron, 2, and so on and so forth. So what we get finally is this image with these discriminated pixels with different amounts of charge. And what we do next is count the number of pixels that have only 1 electron. This is the data that we will use for our analysis. Only the pixels that have 1 electron, we count them, and that will be a number for each of the image that we take. The other important data to take into account is the date and time of the readout start and the total readout time, because that will allow us to compute the incidence angle of the dark matter wind at the moment that the image was taken. And then we can be able to compare it with the theoretical models. So how do we compare? How do we do this comparison? Okay, so we have the data here plotted in red and a simulation plotted here in blue, which tells us what would be the rate of events in our detector in the different times of the day. So we compare the observed events versus the simulated events. And also here I add the mean of these dark matter simulated events, because this mean is what usually you use for a direct dark matter detection experiment. You compare your observed events versus this mean of events. And in this case, for this model, this 1 MeV of WIMP and the scattering cross-section with electrons of 5 × 10⁻27 square centimeters, we could reject this model with the data, even if we don't look for the modulation. But what happens if we lower the cross-section to the half? Well, now our data is compatible with the dark matter events at a mean, with this mean of events plus a little background. But if we look at the expected modulation, well, we see that our data is not consistent with this expected modulation. So now we can reject this model because of the search of the modulation. Finally, we will reach a point at which we cannot reject the data anymore, even if we look at the modulation. And these are the limits that I'm going to report next. So let me stress that the search of the modulation allows us to set stronger limits to the dark matter electron cross-section, even if we cannot reduce our background, as long as the background isn't modulated in the same way as the expected signal. So in order to read the whole skipper CCD, we need to perform our 1 × 5 hardware binning. This means that we need to sum the charge of the 5 rows into 1 pixel and then read this sum. Each image will correspond to a 1 hour and 15 minutes of exposure time. This is the same time as it takes to read the whole CCD. This corresponds to around 5 milligrams a day of exposure per image. The data has begun taking since August last year, so we really have a lot of science data here. But we have observed that we have not enough data stability. There are many fluctuations in the event rate of single electron events that are different every time we take a different run. So in order to well, to analyze the data correctly, we have applied a Gaussianity test. And if the data passed this test, then we included them in the analysis. And in this way, we have 2,500 images to analyze, which is around 3 grams a day of total exposure.
So, sorry to interrupt. Yes. You have about 5 minutes left in total.
Okay, perfect. So these are the limits that I want to share with you. In orange is plotted the direct limits if we don't look at the modulation, only using the 1 electron data. So if you see here in this region, it is very similar to Protosensei. Protosensei has a very similar detector, and they are in this limit is at surface, so it is very similar to us. But by looking for the modulation, we can improve the limits at low mass around one order of magnitude in cross section. So it is very interesting, and it's very exciting to do this type of analysis. Because, well, if we could increase the exposure, the mass, or even lower this a bit more, well, we can be competitive. But let me get into more detail. How can we be more competitive? First, by increasing the exposure, because as I said before, by searching the modulation, we will reduce the error bars of our analysis. And this can be achieved by installing more or a bigger CCD, and we are planning to do this. We already have a bigger CCD in its way. And the second option is to reduce the fluctuations of the events, because well, there are many sources of these single electron events that we see in our images, and we have already characterized some of them. For example, we know that there is some charge generation when we turn on the acquisition board, so we need about 2 days in order to the data to be stabilized. We have a light emission in one of the amplifiers, so sadly this is a background that we cannot get rid of. There are serial resistor events that are very annoying because they leave a long trail of single electron events that are hard to mask. There are some charge transfer inefficiencies. Also, there is a thermal noise because the CCD cannot be at 0 temperature, so well, there are always excitations because of the temperature. There is also spurious charge, which is produced whenever we move the charge from a pixel to the next. These are both will happen in our CCD, no matter the rest of the backgrounds. But the most important background that we have right now is this fluorescence or Cherenkov radiation, or simply charges that spread from cosmic ray events. For example, if we have a muon interacting with our detector, it will leave a trail of single electron events around it. And as we are at surface, this is what is dominating our background right now. And this takes me to the future of the square. We will go underground. We are located here in Bariloche right now, and we will move 600 kilometers to the east towards Sierra Grande, where a similar search was carried during the 90s using Germanium detectors. And in that place, there is an inactive iron mine in which we can access to 400 meters underground. And we are planning to move the experiment to this site by the end of October this year. So stay tuned for that. So to conclude, with this very little, less than 100 milligram prototype detector and operating on surface, we're able to improve the current surface limits to dark matter electron interactions. We're planning to move this detector to an underground site and therefore expect to reduce the background. And finally, I want to stress that similar experiments can benefit from the search for this modulation, as long as they have enough time resolution. Well, that's all I wanted to say. Thank you for your attention. I'll be happy to answer questions.
Thank you very much, Nicolas. It was a very good talk, very nice, very interesting topic, certainly. I know I have a few questions, but I want to give people the opportunity to ask something first. We probably have 2 or 3 minutes. Tarek, go ahead.
Just a brief question. So I understand going underground will help reduce background, but at the cross sections you're probing right now, are you concerned that also it will reduce your WIMP signal somewhat?
Well, it's a possibility, but as I know, for example, this analysis is also ongoing for the Sensei collaboration. That also has Skipper CCDs installed underground, and they already have a very nice prospect for improving their limits there. So as they will be, I think the depth is very similar, and of course we have to take that being underground into account. But I don't think that it will limit our results in that way.
Thank you.
Do we have any other questions? So my question is kind of related. I think, so on slide 18, you showed these preliminary limits. And presumably the modulation limits rely on actually having a modulation in the predicted signal. But as you decrease the cross-section, that the size of that modulation should decrease. So do you know roughly where the direct limits and the modulation limits become equal? When do you stop gaining from the modulation limits?
Yes, that is true. The modulation indeed becomes smaller as you go down into the cross section, and I do not have the numbers. I know that these modulations depend on. I mean, the limits that we're looking for come from a simulation, and I know that these simulations have been carried up to 10 to the minus 35 around this zone of the graph, and that there still exists some modulation. Now, the challenge will be that we can reduce our background in the CCD in order to be able to resolve this expected modulation, so that our error bars are significantly smaller than the expected modulation. That is the challenge right now.
Okay, thanks.
Thanks.
Do we have any last pressing questions?
Only to clarify, I think I didn't tell, but this is for scattering with electrons with a heavy mediator, this plot. Okay, thank you. Okay, I think we can thank Nicolas again, and we can thank all of the speakers for today's session. Thank you very much to everyone. Thank you to everyone who joined. I'm sure the discussion can carry on Slack for those who want to. Otherwise, we'll meet again tomorrow at 4 p.m. In the afternoon. That's Spanish time. Thank you very much, everybody, and I'll see you all tomorrow. Thank you. Bye-bye.
Thank you. Bye.
Thank you.
Bye-bye.